Hello everyone and welcome to this week's lightweight Java game library 3D game tutorial, and this week we're going to be using matrices to move and rotate objects in 3D space, as well as introducing a movable camera. So to kick off, I want to introduce the concept of entities into our program. So I'm going to go ahead and create a new package called entities, and then create a new class in that package called entity. And an entity is basically going to be like an instance of a textured model. So it's going to contain a textured model and also the position, rotation and scale that we want to render that model at in the 3D world. And entities will allow us to have multiple entities that all use the same textured model, which means we'll be able to render a certain textured model many times in the world, but we'll only have to load up the model once. So let's just go ahead and generate a constructor here by going to source, generate constructor using fields, and just click OK. So now we have a constructor, and then we're just going to add a load of getter and setter methods, generate getters and setters, select all, and then click OK. And we're just going to add a couple of extra methods in here to move the entity around. So I'm going to add a method here called increase position that will be able to move the entity in the world, and this will take in an x, y and z value of how far we want to move the entity, and all that we have to do in here is to increase the current entity position by the x, y and z values that we take in. And then I'm going to create another method that basically does the same but for the rotation of the entity. So it will increase rotation, it will basically rotate the entity by a certain amount. Again, it will take in a dx, dy and dz, each of these representing the degrees we want to rotate it around each axis. And then again, we're just going to increase the current rotation by these values that we're taking into the method. So that's pretty much the entity class done. So now we can go ahead and update the renderer to update the render methods so that it now renders entities instead of just textured models. And let's also take in the shader here so that we can upload the entity's transformation so that it renders the textured model in a different position. We're still going to need to access that textured model, so we'll take it out of the entity here by doing entity.getModel. And now we want to load up the entity's transformation, so that's the entity's position, rotation and scale, to the vertex shader, to that matrix, that transformation matrix uniform variable that we set up last week, and that will move the textured model. It will move where our model is rendered on the screen. So we need to create a transformation matrix using that method in the maths class that we created last time, and that's going to take in the entity's position, the entity's 3 rotation values, so entity.getRotX, getRotY, and entity.getRotZ, and also the entity's scale, entity.getScale. So that will create a transformation matrix from the entity's position, rotation and scale, and now we can load up this transformation matrix to the shader using the method that we used last week, that we created last week in the shader class. So load transformation matrix, and that will take in the transformation matrix. Let's now go into the main game loop class and let's create an entity so that we can test all this out. So let's create an entity called entity, and this is going to take in the textured model that we want it to represent, which is going to be our textured quad, and then it needs to know the position that we want to render this entity at, and we're going to render it at -1x00, so that should move the quad one position to the left, and we're not going to rotate it, and the scale is just going to be 1. We need to update what we're putting into the render method. We're going to now render the entity, and we also have to give the shader, and that should work. And there you go, you can see that the textured quad has been moved over in the -x direction. We can also make use of those couple of methods that we put in the entity class. So if we increase the position of the entity in the positive x direction every frame by 0.002, and let's also rotate it so we can see that working. So every frame we're going to increase the position and increase the rotation, and if we run that, you should be able to see that working quite nicely. So the x position of the entity is increasing, as is the rotation. Let's now try something else. If we put this back at 000 and now try increasing the z position by -0.002, so this will move the quad backwards into the screen, and run that, it doesn't look like anything's happening. Let's have another look at the OpenGL coordinate system to understand why this happens. So we've got the x-axis going across the screen to the right, and we've got the vertical y-axis going up the screen. And finally we have the z-axis, which it's impossible to draw here, but you have to imagine it pointing directly out of the screen towards you. So if we look at our quad, changing the z position of the vertices isn't going to have any effect on where the quad is rendered on the screen, because the x and y coordinates are going to stay exactly the same. Now, this obviously isn't very realistic. We would ideally want the quad to appear smaller the further away it gets. So, as we already know, to change the position of the vertices of a model, we need to use a transformation matrix, and there is one special matrix that does exactly what we want in this case, and it's called a projection matrix. The projection matrix basically changes the view that we currently have to something more realistic, like this. This gives us a wider view of objects in the distance, and also makes them appear smaller when they're further away. There are a few variables that we have to decide on before constructing a projection matrix, such as we need to choose the field of view angle, which determines how wide our view is, the near plane distance, and also the far plane distance, which determines how far into the distance we can see. So this is how a projection matrix is constructed, and I'm not going to explain the maths behind it. It's enough for you to just understand what it does, which I just explained. But if you're interested, there are some links in the description of this video. So let's now go back into the code and set up the projection matrix. So in the vertex shader we need another uniform variable, which is also going to be a matrix, a map4 variable, and we'll call it projection matrix. And to apply the projection matrix transformation, very simple, we just have to multiply it by the result of the transformation matrix multiplied by the input vertex position. So now we need to set up some stuff in the static shader class so that we can load values to that uniform variable. So like we did with the transformation matrix, we need to get the location of the uniform variable by calling getUniformLocation and putting in the name of the uniform variable, which was projection matrix, and we'll store the location in the variable location projection matrix. And then when we want to load a matrix up into that uniform, we'll have to call this method that we're creating now, the load projection matrix, which will take in the projection matrix that we want to load up, and then we can load it into the uniform by calling load matrix, which will take in the location and the matrix that we want to load up. So let's now go into the renderer class and actually set up the projection matrix itself. So let's declare a matrix4f variable up here called projection matrix, and we need to have a few constants defined, such as the field of view angle that you want your projection matrix to have, to define the exact shape of the frustum that we want to create. So I've set the field of view to 70. I'm going to set the near plane variable to 0.1, and I'm going to set the far plane variable, which is basically how far you can see into the distance, I'm going to set that to 1000 for now. Then we need to actually create the projection matrix itself, so let's create a private method down the bottom here that will initialize the projection matrix itself. And I've actually got the code for this copied because, as I said, it's not overly important, so I'm not going to explain why this is the code or how the maths works, but as I said, there are links in the description which will explain that sort of stuff to you. So just copy that down now, and we need to call this method at some point. So let's now create a constructor for the renderer class so that the projection matrix is set up only once, because it only needs to be set up once, it's never going to change. We'll set it up right at the beginning when the renderer constructor is called, and we'll also take in the static shader because we want to load this projection matrix up straight away to the shader. It only ever needs to be loaded up once right at the beginning because it's never going to change. So we'll start the shader, then we'll load up the projection matrix, and then we can stop it again, and then we never have to load that projection matrix up to the shader again. It will stay there and it will work every time. Now in the main game loop we need to change this a bit. We actually have to put that after creating the static shader now, so that we can put the static shader in as a parameter, and that should now work nicely. So let's go down here and we can test that out. Let's move the entity, let's render it initially at -1, and then let's move it back a bit faster. And let's try that, and there you go, you can see it zooming off into the distance there and getting smaller as it goes. Now there is one final factor that changes where an object is rendered onto the screen, and that is the camera position. As you can see here, the camera is moving to the left, which is causing all of the rendered objects in the world to move right across the screen. Now, it's important to remember that when we're programming our game, there is no camera. This is just a simulation on a computer. There is no man holding a camera that we can move around. The OpenGL coordinate system isn't going to change. The center of the screen is always going to be 0, 0, so we can't actually change the viewpoint of our game. What we have to do instead is to simulate the camera moving by actually moving all of the objects in the game in the opposite direction. So what's happening here is not that the camera is moving to the left, because there is no camera, but the whole world is actually moving to the right to make it look like the camera is moving to the left. So to move all the objects, we're obviously going to need another transformation matrix, which will represent a transformation that is the exact opposite of the camera's transformation, and we'll apply this to all the objects in our game. This matrix is known as the view matrix, and we'll update this matrix whenever our camera moves, or once every frame to be safe. So back in the code, I want to create a new class called camera, which is going to represent our virtual camera. So the camera is going to have a position, of course, and that will just be a vec3, and we'll initially set that to 0, 0, 0. Then the camera also needs a rotation around the X, Y, and Z axis, or this is also known as the camera's pitch, which is how high or low the camera is aimed. The camera's yaw, which is how much left or right the camera is aiming, and the camera's roll, which is how much it's tilted to one side. So if the roll was 180, the camera would be upside down. A quick constructor, don't really need that actually. And now let's have some getters. So select getters and click OK. And I don't know why they're all protected. Make sure that you've got yours as public. And I'm also going to add a move method here, which we can call whenever we want to move the camera around. So we'll probably call this every frame, to move the camera every frame. And we're just going to check the keyboard inputs here so that we can move the camera with our keyboard. So I'm going to check if the keyboards, if the key W is pressed, and if it is pressed, we're going to move the camera in the -Z direction. So we're going to change the Z position of the camera. We're going to make it 0.02 less. Then if the D key is pressed, we want to change the camera's X position. We want to increase it by 0.02. And finally, if the A key is pressed, we want to decrease the camera's X position to move it to the left. So now we want to create the view matrix from the camera's position and rotation, and to do this we basically do the opposite of what we would usually do, because we want everything to move in the opposite direction. So I've got the code here actually just to speed up this tutorial, but all we're doing is we're creating a new matrix. We're then rotating it first instead of translating first, because it's the opposite way around everything. And then we want to make the position negative, because we obviously want to move the whole world in the opposite direction to the camera. And we're then translating the matrix and then returning it. So that will create the view matrix, which is the opposite of the camera's position and rotation. We'll then want to load it up to the shader program every time the camera's position changes. So we'll have a new uniform variable called view matrix, and we have to multiply it in like the others, but it has to go in between the projection matrix and transformation matrix. Then again, in the static shader we have to do our usual setup. So create a variable to store the location of that uniform, and then we have to get the uniform's location, and the uniform is called view matrix. And then of course we need a method to load up the view matrix, which we will call load view matrix, and this is actually going to take in the camera, and we'll create the view matrix in this method. So it takes in the camera, then we'll create the view matrix from the camera. So matrix 4f view matrix equals, and then we'll use that method in the maths class, create view matrix, which isn't there. Just have to save it first. No. Oh, I didn't make it static. Don't forget to make it static. Yeah, so view matrix equals maths.create view matrix. That takes in the camera. So we've now got our view matrix, which is going to move the whole world in the opposite direction to the camera to simulate a camera, even though there is actually no camera. And then we'll load up that view matrix to the shader. So let's go into the game loop to test all this out. We need to create a camera that we can use. So we'll create a camera called camera and call the constructor, and just import that. There we go. And every frame we are going to want to load up the camera or the view matrix to the shader. So let's call shader.loadViewMatrix. That will move the whole world to make it look like we're moving the camera. And let's actually move the camera every single frame. So we'll call camera.move, and that will take in the keyboard inputs. Let's try that out. And yeah, you can see that that's just about working. It's a bit hard to see because this cube, the square, is moving back so fast. So to make it easier to see, I've created a cube. I've written down all the vertices and indices and texture chords, and you can find all that data in a text file which I've linked in the description, so you don't have to copy all that down, so you can just copy and paste it. Let's now render the entity at -5z so we can see it a bit better. Let's not move it backwards, but instead let's rotate it by calling entity increase rotation and rotate it around the x and the y axes, and then go ahead and run that, and there is a cube, but it looks all crazy, and that's because the triangles are just rendering on top of each other. We haven't said which triangles should render first, so they're just rendering in a random order. What we do need to do then is to tell OpenGL to test which triangles are in front of each other, and we can do that by enabling the depth test. So OpenGL will test which triangle is in front of which and then render them in the correct order. So GL depth test, and we need to clear the depth buffer every single frame by putting that extra bit of code in there. And if we go ahead and run that, you can see a cube rendered nicely and rotating in 3D space. So that's it for this week. Next week you'll be able to load up your own models that you've exported from Blender or other 3D modeling programs, because we're going to be creating an OBJ file parser. Don't forget to check out my latest devlog video for my game, link is on the screen now, and keep in touch and stay up to date on my social media sites, links are in the description. But yeah, thank you guys very much for watching this video. Do subscribe if you haven't already. Have a great week, and I will see you all next time.